windowing and tell you why windowing is so important. But first, I'm going to tell you an application of why windowing is so important. Now, you don't have to write this down. If you listen, this is something that's not in the text, but it's useful. If you say windowing, what does it really do? Well, it gets rid of side lobes. Why are side lobes a problem? Here's why. If you listen, you'll understand. Hopefully you'll appreciate it. And this has to do with something I work in this area. It's radar. I hope this one works. I usually have one or that's one. This is radar. Now, if you follow me on this radar, you have, and this is called monostatic radar, this is standard radar, you have something that's going to send a signal. And there's something out here called a target. Now this target is usually moving with some velocity v. The target is at a certain range r. Now some of you have had electromagnetics. If you haven't, don't worry about it. Just for now, assume this is sending a signal. The signal is going to go and strike that, and it's going to return, be reflected. That's the idea. It's just like a bat with echo detection. So what does the signal look like that it sends? I'm going to assume this is going to be an electric field magnitude or a power magnitude. I can't get into every aspect of this, but it has to do with, let's just say it's the actual power magnitude of the signal. When you look at the actual signal that's transmitted, this is the radar, call it P transmitted, just P tran, right here. What it looks like in time is this. There's some period called the on time that is designated tau, and then there's a point at which it repeats itself. This length is capital T, it's the period, and it keeps repeating itself on and on. Just try to understand. I don't want to get too involved in this, just give you an appreciation of what goes on. This is called the envelope of the signal. It's called baseband. It just shows you the envelope. Now this thing is multiplied by a very high frequency signal, a cosine signal. So in here, there may be 10,000 to 100,000 cycles. Follow me? So it's really taking a snapshot of something, and this is what is actually energizing, or what's considered the power or voltage on this antenna, and it's launching an electromagnetic wave. That's what you have to appreciate. The E field is actually in this direction. It's perpendicular to the path that the actual wave travels. It strikes this, and then some of this is reflected. Some of the signals reflected. That's the idea. Are you with me? Giving you a very basic overview. Now, there's a couple things I have to tell you about this, and I'm going to get to why windowing is important, but you have to appreciate the problem. When you take a look and you send out something like this, I've isolated only one target. In truth, in the real world, this radar beam is not just going there, it's going in a lot of directions. It's hitting the ground. Some of the ground is actually reflecting back the signature from the ground. There may be other targets out there. So keep in mind, I'm oversimplifying the problem, but you'll appreciate why in a second, hopefully. Now, how far away can you see this target without the range being ambiguous? Let me follow me on this. The wave is moving out the speed of light. Do you agree with me? Everybody with me? It's moving out the speed of light. It goes a distance r to the target, and then the reflected wave reflects back. In order for us to see it, we have to see the reflected wave. So the actual distance it travels is 2r. Do you agree with me? I'm just going to put this over here. So 2r is the actual distance that the electromagnetic wave travels. It travels that at the speed of light, c, which is 3 times 10 to the 8th meters per second. And there's some time it travels. I'll just call it t1. Now, what is t1? It's equal to 2r over c, right? You follow me on that, everyone? Now, if we have this, and this is normally a much shorter duration signal than I'm showing. It's maybe 1/10 of capital T, the period. But if I send the wave out at this point, and it's launched, and it hits, then returns back, if it doesn't return back before the next pulse is sent, I don't know which pulse caused it. Does that make sense to everybody? So there's a thing called the maximum non-ambiguous range, and I'll tell you how we actually account for anything out further than that later. But for now, just understand, the furthest range that we can actually detect that's non-ambiguous is going to be the point where really this T1 is equal to T, the period, and that's equal to simply 2R, really, I should say, the maximum non-ambiguous range would be equal to C times the period, or the actual period T divided by 2. And that's called the maximum non-ambiguous range. So this is non-ambiguous range. Now, trust me, I'm trying to make sure you understand that. If the target was further than that away and it struck it, you wouldn't know if it was this pulse or this pulse that caused the return. You all with me on this? Now, the truth is, we can approximate the size of the targets we're going to see. We're not going to see things that are the size of Yankee Stadium that are solid, metal out there generally. There's smaller targets than that. So at least we have some concept of this size. So we can figure what the power is that's going to be reflected back. Now, power, if you know, how many had EMAG here? Physics, did you have physics, electromagnetics at all? Yeah. Power falls off as 1 over the distance from the target squared, all right? And that's electromagnetic power or sound power. Once it strikes the target, only a very small portion of that power is reflected back, and that power also falls off as 1 over r squared. So you get a 1 over r to the 4th, where r would be the range to the target of power fall off, and it falls off in a way it's proportional size of the target. What that really means is that say that the maximum non-ambiguous range was set at 1 mile. If there was a target 2 miles away, it would have to be ginormous in order to get any meaningful power back. So they can eliminate a lot of this target ambiguity simply by understanding the proportions of the target, the likely size. Follow me on this, guys? And I'm trying to make it oversimplified. Now, so at least if we took a look at this as the transmitted signal, and we superimposed on that, and I don't have a red marker here, but saying right below here, we superimposed the return, and all of a sudden the return came right, say, here, like this. Then we could get an estimate simply by the delay from the time it's sent to the center point of that, the distance to the target. That should make sense to everybody. It's a simple ranging thing. You with me on this? All it means is this. If you know, say, the speed of sound, right? What is the speed of sound down here? 86 miles an hour, roughly? Well, how many feet, 780 feet per second, is that right? What's the speed of sound? 700?
I looked up.
Anyway, it's not that fast. So if I and I listen for an echo, 1,200, 5 seconds later it comes back, right? I know the distance to that point is really going to be what? The velocity of sound times the time delay divided by 2, because it went back and forth. That's the real essence of what I'm showing you here. Only it's now going to be the speed of light involved. Do you follow me on this, everybody? Yeah. This is much, much shorter duration here, right? And they usually look at the center points on this, but don't worry about that for now. All right, now that is simple ranging. That's called a monostatic radar that's doing ranging. The thing that everybody uses radars for when they're looking for things that are threats are called moving target indicators. If you've ever got a ticket from a police officer, he was using a Doppler radar called a moving target indicator, where they looked at the rate of change of your velocity with respect to the police car. And if the police car is standing still, it's pretty simple, but they can actually see what it really is called a Doppler shift. Have you heard of Doppler shift, everybody? If you have, raise your hands. You heard it in physics, didn't you? What is Doppler shift? This is simple thing. Has to do with either the shortening or elongating of the fundamental wavelength of a transmitted frequency because of the motion of something that's reflecting it. Now, when you hear automobiles coming at you, if you've ever been to a speedway, you hear, and when they leave, you hear, now the RPM didn't change. What happened was what? The wavelength elongated because the thing's moving away. If it's moving towards you, it's shortening. Are you with me on this? That's basic Doppler. Think of it that way. So how do we get Doppler velocity? How does this velocity affect the Doppler spectrum? The Doppler spectrum is where windowing is so important, by the way, and that's what you're going to see. Well, think of it this way. Targets out a distance r, right? All right. Now, if I send sound, it goes out. Send electromagnetic energy, goes out, strikes the target, and comes back. The total distance it travels is 2r. Do you give me that? So just work with me on this. If the total distance is 2r traveled by the wave, this is very simple. I'm not going to go and do anything complicated. The number of wavelengths in that, I would have to divide this by the number of wavelengths. Now I know the number of wavelengths that the actual electromagnetic energy traveled at a certain frequency. Does that make sense to everybody? I'll show you why this is important. Now each wavelength has what? 2 pi radiances in it, doesn't it, class? So if I multiply this by 2 pi, now I have the total phase change that the wave would undergo from the time of transmission, in a very simple sense, to the time it's received back from a reflected target. Are you with me? And there's a transmit and receive mode. Normally with radars, you transmit, then you throw the switch back to listen. As soon as this pulse is done, you go to a listen mode, and now you're receiving energy back, and you're recording all that energy, you're sampling it, you're digitizing, and you're storing it in what's called bins. Bins are length of the actual window. I'll get to that in a second. And that keeps going until this next one's about to transmit it. Then you flip to the transmit mode, and you transmit, then you listen. Transmit, listen. That's the way a monostatic radar goes. And it stores all this. What most radars are looking for is something moving. The only ones that are really not looking for that are things that are ground penetrating radar that are looking for like mines or, subterranean oceans or something like that. Almost all radars, modern radars, are always looking for the Doppler shift. Does anybody work with radar at all in here? Have you worked around radar or anything like that? Nothing? I usually have one person or two persons that have. So if this is the phase, that's the total phase that's changed from the time the wave is sent to the time it returns for a given frequency. What do you expect? How would you expect to find the shift, the Doppler shift in that phase? What would you do? Take a derivative of that with respect to time. Now, if I take a derivative of this, this is actually equal to what? It's equal to 4 pi over lambda r is the total phase, and the rate of change of phase with respect to time would be 4 pi over lambda times dr dt. And that is what's called the Doppler shift in radians per second of the waveform. You can write that down. You'll see this again and again. It won't be just in this class. You'll see it in EMAG. You'll see it in some of your other courses. That's the Doppler shift. It's in radians per second. Most of the time, we say that's equal to 2 pi times the actual Doppler shift in hertz. It's f sub Doppler. Are you with me? Just work with me. I'm going to show you a few things that are very, very important to get an idea of scale. So if that's the Doppler shift right there, then if I take a look at f Doppler, work with me here, you see I can divide that 4 pi over lambda by 2 pi to get rid of it out here, right? To just get f Doppler. Everybody see that? Can you see it? Remember, that's omega sub d. That's like omega is radians per second, right? Radians are 2 pi f, right? F is in hertz, cycles per second. So then I can get, if I divide by 2 pi, now I get simply 2 over lambda times v, and this is going to be v Doppler, or actually the velocity, I'll just call it v target. V target is velocity of target in direction of radar. Let me explain why I'm putting it there. And lambda is the wavelength. And wavelength, lambda is equal to c over the frequency f0, and f0 is the high frequency. Radar signal. Now, which means is this, all those cycles are at f naught. F naught is typically of the order of, say, a gigahertz, 10 to the 9th to 10 to the 10th, or 10 to the 11th hertz. High frequency. Your police radar, the old K-band units were about 10 gigahertz. The new K8, if you have a radar detector, you know what I mean. I don't endorse or condemn them. K8 band is about 33 gigahertz. All right. And if you go up north, you get KU band. You're going to get a few other different bands, but does anybody here own a radar detector? I want to say you're not telling me the truth, but I wouldn't do that to you guys. Well, I own one. I teach radar. If I don't own a radar detector, I look like a fool. Yes, and I use it for all sorts of things. Anyway, with this said, now take a look at this. This is the Doppler frequency. That's the shift available. I want you to think of something. We send out a signal whose base frequency here is gigahertz, right? I'll get to it. When we've got a gigahertz signal multiplied by some pulse, repeating pulse waveform, right? The pulse waveform we know is going to have a sinc function. You already with me on that? When I look in the transform. The high frequency cosine wave multiplying that sinc causes the actual centers of those sinc functions to be at plus and minus f naught in the frequency domain. I'll get to this in a second. That should make sense to you, right? Now the first null, when you think about a waveform, if you think about the sinc waveform, there's a first null we could figure by setting the sine equal to what? Well, I'll do that, but we can figure out where the first null is. If that first null that occurs is greater than the Doppler shift, we're never going to see this target. Are you with me? And I'm going to show you this, and then I'll show you what windowing does for us. Now, if you look at this just for a second, let's do something typical. Take a typical Ka band radar at 30 gigahertz. Are you with me? Now we're going to say that F naught, for my example, is about 30 times 10 to the 9th hertz, or 3 times 10 to the 10th hertz. That's 30 gigahertz, that's about Ka band. You can write this down. I'm not saying anything here that's going to get me in trouble. It's about Ka band, not quite. Now if that's the case, I have two, wavelength is C over F, correct? So I can put C down here, which is 3 times 10 to the 8th meters per second, divided by F. I can put F up here, which is 3 times 10 to the 10th, right? Times VT. And I have 2 times, well, 3 times 10 to the 10th over 3 times 10 to the 8th is 100, or 10 squared, right? So it's 2 times 10 squared times VT, or it's really going to be 200 VT is going to be the actual Doppler shift. Are you with me, class? Think about this for something, and that velocity is in meters per second. Now, how fast are you going in your car? If you're going at 80, say, 60 miles an hour is what? 88 feet per second, isn't that right? And how many meters per second is 88 feet per second? Call it 90. 90 by 3 is about 30 meters per second. Do you agree with me? Guys,
Yeah.
Are you with me on this? I'm just trying to give you an estimate of what a Doppler shift would be for a moving car. Not a missile, that's much different, or any kind of satellite. I'm talking about something, a moving car. So now we're talking about a Doppler shift here for a typical car, and I'll put car, being equal to, for a typical radar, K-band radar, of 200, right, times 30, or you're talking about 6,000 hertz. Are you with me? 6,000 hertz of shift. The center frequency for our transmitting frequency is 30 gigahertz. 30 gigahertz plus or minus 6,000 hertz ain't much. Are you with me? 30 times 10 to the 10th versus 6 times 10 to the 3rd. That's a negligible amount. Do you follow me on this, class? So how do you distinguish this? I'm going to get to this. This is interesting. And I'm going to do it, try to do this without, doing all the high-level math that is really required to do justice to this. I'm trying to give you the overview. So now, you're going to see. One other thing I can tell you is, with any radar operation and stuff like this, what you have is a lot of other noise sources out there that do nothing for you and you'd like to get rid of. There's all sorts of things when you look at the spectrogram of these things that are irritants. They tell you nothing and you would like to get rid of them. So now, why are windows so important? So I'm going to try to do this. Remember what the radar signal looked like when it was sent, right? It's on for a time, off, on, off. All right, when it comes back, it's really a scaled model of that, maybe down 10 orders of magnitude in terms of the power, but the time interval is the same. And it's sampled and stored. Remember that, sampled and stored. So now we take a look at an actual radar signal. First we start with the standard windows. This is standard windows, and this is just going to be a plain window, just WN of N. And that's simply going to be 1 for N greater than or equal to 0, less than or equal to L minus 1. This is the standard pulse waveform. And it's 0 else. Now the truth is, with this window, we're going to have, after that signal's sent, every so many seconds, what we're doing is sampling the return, and then we're going to multiply that the return by the window, this window, right, starting at n equals 0, and then we're going to take those values and store them. Then once you get the first window back, you might say the first time interval, then the next time interval is going to be multiplied by the same window but stored in a different area. Follow me on this, class? Just get an idea. I don't want to make it too complicated. Everything that's coming back is going to be chunked into time intervals over that time interval that's predetermined, which is really going to be L times the actual delta T between the samples. And I'll get to that later, how you actually figure that out. Then that's stored, and after that's stored, then it's processed. Are you with me? But first I have to talk about this window. This is going to be what the window is. It's either on or it's off, and that's a pulse, right? Do you remember what the transform of that looked like? Briefly, you don't need to write this down, I'm just going to do it for you. If you looked at the Z transform of this window, this is a standard window, it's linear, there's no taper to it. That would be equal to the summation, and would be for n equals 0 to L minus 1, and then it would just be Z to the minus 1, or Z to the minus n. The reason it's that is because for all other values of L, the coefficient here is 0. That's a standard Z transform definition. Usually it goes from what? 0 to infinity, correct? And then here is going to be the function of n, right? The function of n is only 1 up to L minus 1, so I don't even put it in. When you look at this, remember from last time, this is going to be equal to that to the 0 power 1 minus this to the L minus 1 plus 1, or Z to the minus L over, and then 1 minus Z to the minus 1. Do y'all remember how to do that, guys? This is that standard thing where we had what? We had a series solution, right? This is the summation of series. This is geometric series. Y'all remember this, guys? We get down to this point, and here I do the thing where I pull Z to the minus L over 2 out in front, and I get Z to the L over 2 minus Z to the minus L over 2 here, and then I get Z to the minus 1 half here, and it's times Z to the 1 half minus Z to the minus 1 half. And then I simply replace Z here by E to the J omega, and in doing that, I get E to the minus J omega L over 2 divided by E to the minus J omega over 2 here, and then it's going to be times the sine of omega L over 2 here divided by the sine of omega over 2. Now, the reason I can do this, I'm going a little ahead of myself, but when I substitute E to the J omega here, then I get E to the J omega L over 2 here minus E to the minus J omega L over 2 here, and I know that'll come down to 2J times the sine of omega L over 2. Do y'all remember this, guys? All right, I'm just trying to whiz through this without spending too much time, but I need to at least tell you this. How many remember going through that? Y'all remember that? It's the second or third time I've done this, right? Get down to this point. Now, that is going to be my transform. It's the normal window of omega here. Some of you have actually done this a couple of times. Now I take a look at this and only plot the magnitude of Wn of omega here. So you can take a look at it versus omega, and it does this. The height of this is going to be L. If you look at this, if you just take the magnitude, it's really the sine of omega L over 2 over sine of omega over 2. If you take a derivative of that, evaluated at omega equals 0, you're going to get an L over 2 divided by 1/2, where simply L would be the peak value right here. Are you with me, class? Without me doing L'Hopital's rule on it. Are you with me? Because you can't evaluate it at 0. You got 0 over 0. It's indeterminate. You have to take a derivative. So the magnitude of that is L. Now this is important. The magnitude of this point is 13 dB below. So this one is going to be minus 13, actually 0.26 dB below this point. And do you remember what a dB is? How many do? All right. I'm glad I asked that question. Because I'm so used to assuming everybody knows what dB means.
It's log 10 of your amplitude, isn't it?
Well, I'm going to show you. If power, it's 10 log of the amplitude, but for a voltage or current, it's 20 log of the amplitude. I'm going to show you right now. This is going to be good for everybody. You'll be using this. Write this down. You're going to need it. You won't graduate engineering if you don't know this, or not likely at least. So now come over here, and you'll see why the windows are so important with radon. Now, for dB, this is decimals. The symbol is dB. A dB is 20 times the log of a voltage, or 20 times the log of a current. And it can be a current ratio. It can be a ratio of two things. Are you with me? It's also a dB, and if it's power, it's 10 times the log of the power quantity. And the power, of course, is in watts. Are you with me, everyone? Now, when they say something is down by 13 dB, what they mean is this. If I go ahead and I say minus 13 dB is on this side, minus 13 dB is equal to 20 times the log of some quantity A. What we're going to do is find out what the ratio is, how far down it is. So if I divide 13 by 20, I get 10 to the minus 13 over 20 here is equal to actually A, isn't it, class? You would divide minus 13 by 20, and then you would take both sides to the power 10 of its log base 10. What is that quantity equal to? Can somebody just tell me? It's actually 13.26, but don't worry about it.
It's like 0.223.
All right, what it really means is this point here, the second side lobe, is about 1.223 L in terms of its magnitude. But it's still significant. It's over 20% of the peak value. And this one down here we can figure out too, but don't worry about that. That's the next side lobe you worry about. Now, what we'd like to do with windowing is get rid of this. Other thing I'm going to say here, just to put this in perspective, and I don't want to dwell on this. If you remember before when we did the DTFT, one thing we talked about is comparing a DTFT to a Fourier transform. How many remember that? You did an assignment with that if you did the extra credit, right? One thing you found out, don't dwell on this, because I'll spend. When I looked at omega here, omega was actually equal to 2 pi divided by n. Well, and then it was times k here, where n's the number of samples. Do you all remember doing this, class? How many remember actually taking the actual number of samples and the time interval between samples and stuff, and turning this into a small, I'm going to actually put a small omega here so you'll understand. If it's a small omega here, it's omega sub k, and I'll put small omega here, omega sub k here, then this is divided by t, sample, also. Now T sample is the same thing as T, the time interval between the actual pulses sent. Y'all remember this? First pulse goes, then second pulse. That's the T that would go here. You can calculate this frequency, but that would be the frequency that you see on this axis. Are you with me? We have to divide it by 2 pi if we want it in F, but that's it in omega. Just try to understand, I'm giving you some perspective on this, how you do it. You know, I'll fill in a lot of the gaps in a second. I need to put the whole overview up. So now, this is what this looks like. I mean, this right here is the spectrum of the window, right? The DT-FT spectrum of the window. Follow me on this, guys? Everybody? And remember this, when we do the sample, we're going to have this on for a small period of time, whatever it is. It's really going to be L times the sampling interval. The sampling interval is going to be very fast. It's going to be about maybe 1/100th of the actual time interval between pulses, 1/100th of that. We take that, and then we turn that into a true DT-FT, and I'll show you what we do with that in a second. But the problem is always these sidebands, because what happens is with these sidebands, if you do have a moving target, and suppose this is the actual signal that you would have if the target didn't move, all right? That's called the actual original signal. When the actual signal shifts, this whole spectrum shifts. But if these sidebands aren't suppressed, then they look like moving targets too. It looks like multiple moving targets. Are you with me, class? And they hide the actual essence of where the moving target is. And I'll try to be more clear about this. So, that's dBs. Now, here's what happens. We want to get rid of those sidebands. So I'm going to go right to the best window to use. It's called we could go to the triangle waveform and the Bartlett's waveform. Let me do one thing before there's a workup to it, because it's been a while. All right, I said that the actual window W sub, you don't need to write this down, of n was 1 for n greater than 0, less than or equal to L minus 1, and L is the length of the pulse. Then I said that it's 0 else, right? 0 else. Then I said this, for the spectrum of this, looked like a magnitude spectrum, forget about the phase business, is the sine of omega L over 2 over the sine of omega over 2. That's, you might as well put a magnitude here. And that looks like about a sync waveform, if you remember that. We talked about that, right? Then what we talked about is the width, null-to-null width. This is the next thing I need to talk about. Well, that width we got last time, if you remember. We said what? I know this top part is changing much faster than this bottom part in terms of omega, right? Because it's multiplied by L, right? And I said this argument equal to what? To find the first null.
Pi.
He's right, pi. Do you remember that? That's equal to pi because if you think of a sine waveform, it starts at 0, at pi over 2 it's 1, and then at pi it goes back to 0, right? So if I set that equal to pi, that means 2 pi over L would be omega where the first null is, right? But the total width of this, if this is 2 pi over L, this is minus 2 pi over L in terms of that was centered at 0, this width here would be 4 pi over L. Are you with me? Please just bear with me. That's a critical factor, 4 pi over L. Now, that's a window with just one. If I take, next I have to do it this way. I'm trying to do this sequentially. I didn't mean to use the whole class grid for this, but I need to. The next thing I want to do is multiply that by the cosine waveform. You remember the cosine is a very high frequency waveform, right? You all with me on this? So now I take, and I'm going to say my signal, that's the window. The actual signal I'm interested in, I'll call it S sub W of n, is going to be equal to cosine of omega naught n times my window of n sub n. And that has a transform. It's really, since that's a cosine right there, it would be have a transform. This is going to the frequency domain of 1/2 times the transform of the window, W sub n of omega plus omega naught plus the transform of the windowed function of omega minus omega naught. Are you with me so far now? This will get the point across. So now when I take a look at what happens, that's what the window looks like. I'm not even going to bother with going to the actual frequency, the frequency range that we're talking about yet. When I look at this in the capital omega domain, I'm going to have two frequencies. This will be omega naught minus omega naught. And let's just take a look at the magnitude of the actual transform of that. And now I'm going to get this. I'm basically getting this. This still has a width here of 4 pi over L. And this has a width of 4 pi over L. And this is still down minus 13.26 dB from the actual peak value right here. That's what you need to get from this. Are you with me? Now, just so we keep our mind on what really we're interested in, when there's a Doppler shift, this is either going to move downward if the target's moving away, or move upward when we get our received signal back. With me? And in order for us to really see this, we have to eliminate these things right there. If we don't eliminate them, we won't be able to distinguish where in fact the target is. And in fact, we would like to get this as narrow as possible. Do you see one thing right here that would narrow that lobe? Just look at this for a second. What would cause this to be narrower? Take a look at what does L indicate? The length of the sampling pulse, right? We would like that to be as long as possible. The downside of that is this. The longer that is, the less resolution we have of exactly where the target is centered at. Right? We'll know approximately where it is, but we lose the fine detail the longer that pulse is. There's always trade-offs. So that's something. Now, for now, just go with me there. Now we're going to take a look at what happens when I take this same function. Something to remember too. What I'm doing here is I'm stripping out so much, but you know, when you send a signal and it's coming back, I'm going to start, and I have my stopwatch, and I turn it on, and I'm sampling at a certain rate, TS, or a certain sample interval, ding, 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 all the way out to L, and all that information I'm going to grab and store digitally somewhere. Then as soon as I'm storing that first pulse is done, immediately I'm starting to sample the next pulse, and I store that, and then stick it back down there in another memory bank, and I'm sampling the next one. Are you with me? So all this is going in concurrently, but we always start our clock when we do this sampling at some n equals 0 when we start these things. Are you with me? Just for simplicity. And we keep information down in what are called bins. Each one of these things, each time we start this process over again, we store it in a different range bin. Just listen to me on that, all right? That's what you need to remember. Now we take a look at what happens when we use a window. I'm not going to use the triangle window. I was going to, but I don't have time for that. I'm going to go to one, probably the most popular window that's used, and the reason is it gets rid of side lobes so that you can see moving targets. And it also, believe it or not, doesn't broaden the main beam ones. So the next thing I'm going to talk about is really the best window. It's called the Hamming. This is going to be the Hamming window. It's named after the fellow named Hamming. He found that if we allow a window, this is Hamming, HM, I believe in the book, W sub HM, it's going to be equal to, and .54 minus 0.46. I use this one, by the way. That's cosine of 2 pi n divided by L minus 1. Remember, the pulse has a length, a number of samples L, and is the actual increment on the individual pulse. What this looks like, a Hamming window actually looks like this. If you just call it windows of Hamming right here, then, and you looked at it, it does this. I'm just going to assume it starts here. It looks like this. Starts at a value I'm not sure if it's 0.2, something like that. Then it reaches the maximum. It looks about like a cosine. If you just assume that's about a Hamming window if you actually take a look at it. That's what it is. If you multiply this window, and remember this is a discrete point, so their values here, by the recovered pulse, and remember it's really going to be what? This window here, the Hamming window here, this is what it looks like in time and in frequency. I'll show you what you get. Come on, 2 minutes. I thought about how to present this. If I can show you why windowing is important, I figure I can make you interested. And the reason is we're looking for a Doppler shift. That's my goal. I want to see the Doppler shift, and I'll even show you why you won't be able to see it when I give you some real concrete examples. So, now, if we take a look at the actual Hamming window being applied to the cosine, well, I'll first just take it without the cosine pulse, and I look at it in the frequency domain. When I look at this spectrum, this is going to be the Hamming window as a function of omega. Magnitude, it looks like this. This is in your book, by the way. It looks like this. This side lobe is down minus 43 dB. It's almost non-existent. Minus 43 dB. However, the main beam width here is now approximately double. Now it's 8 pi over L. Remember before it's 4 pi over L? So the cost of using a Hamming window is it widens the main beam, but it knocks out the side lobes. 43 dB down from the main part is virtually non-existent. That's like, it's a factor of 10,000. All right, if you're 1/10,000th the value of the main beam, it's just about off the charts. All right, that's the way you view this. Are you with me? Because when you're talking about 40 dB, that's a factor of 10,000. You're at 43, you're more than that. Got me on this, class? That's the benefit. What that really means is now, we don't even worry about these. We take a look at this. There's the main beam, right? Now, there's noise and stuff, but everything's suppressed by at least 43 dB out of that main band. So what you get is this, and you're going to use a lot of pulses, right? We're going to have L very large, we're going to have a sampling interval very small. So now that Doppler frequency shift of only 40, what was it, 6,000 hertz? 6,000, 8,000, pardon me?
600.
No.
It's 6,000.
It's at least 6,000. Believe me, if you get 100,000 hertz and you can see it, then you're talking about military-grade radars. They're not cheap ones the police use. You're not going to find that's a world-class kind of solution. When you get about 6,000 hertz, that's about the limit. That means this width here, after everything is accounted for, the shift to the first omega and then F domain will be will be something of the order of 5,000 hertz. Now you can see this point move, and they can determine your actual velocity very easily. I'm going to get to that next time. I had to give you like a workup, why it's important, and I wanted to do it on the board. I didn't want to do it with PowerPoints, just so you appreciate why windowing is so important. It gets rid of all the side nets. But why is that important? It's not for the actual range. It has to do with the velocity of the target, because now when this thing shifts, as the target's coming at you, it'll shift up in frequency. When it's going away from you, it'll shift down, this entire spectrum. And we can look at this spectrum real time, and we can tell, in fact, where there's a moving target with respect to yourself. And if you're an aircraft especially, anytime you see something moving to you at a high rate of speed, that sets off alarms. You've got a problem. Either it's an incoming missile, or it's somebody who went nuts, or it's a non-compliant UAV, but you're in trouble. That's where you just, run for the hills kind of deal. Because collisions does anybody here fly small planes at all? You do?
Yeah, I have.
Are you got a license?
My dad does.
Well,
Sorry,
is this a prop plane?
yeah, it's a 172.
Do you have a radar or not?
No.
All right. Well, when you have any kind of a commercial aircraft, a jet aircraft that is required to take radar, has radar, when you see the moving target indicator coming on, it means something's coming at you. that's when the guy just goes into evasive action. You usually don't have but an instant, because the worst thing is this. You got two planes coming at each other, something like this. The rate of closure is about twice the velocity of one of them, typically. You only got instants to do something, and the standard evasive move is not to, throw on the brakes. It's this, is to go 90 degrees to your path. That's the thing that everybody does. And that's the thing to remember in a car accident too. You slamming on the brakes is great, but if you're gonna hit a tree, you don't just slam on the brakes. You go 90 degrees to that path so you don't hit the tree, and that's the thing with pilots. I have friends that are pilots. I'm gonna give you one that's gonna give you, huh?
No.
You hit a tree?
You don't go into a tree, you just